we've got this sort of budget for CO2 today. And there is CO2 coming out of smokestacks, and that's about 7 gigatons of carbon per year. And sort of deforestation, releasing 2. Now, for comparison, one thing that I forgot to put in this budget last time is the natural CO2 degassing from volcanoes. Because sometimes you can even read people saying that the CO2 going up in the atmosphere is not because of human activity. Not so much anymore. But you could still see this, 10 years ago or something, people even disputing that the CO2 in the atmosphere, that rise is coming from people. Whereas we now know that we're putting in twice as much CO2 in the atmosphere as is required to explain the atmospheric increase. So the atmospheric increase, the evidence for that was this wiggly curve of CO2 concentrations from Mauna Loa or other parts around the world. And so we saw this thing actually animated. You could see the biosphere breathing. This is an annual cycle. And then this upward trend is the CO2 in the atmosphere. And this is only about 4 gigatons of carbon per year. So we're putting in 7 plus 2. We're putting in twice as much as we need to even explain the atmosphere. Oh, volcanoes. I started on volcanoes and I got distracted. Volcanoes are releasing about 0.1 billion metric tons of carbon per year. So, the human sources are much bigger than the natural source. Plus, in the natural world, the natural CO2 degassing would be balanced by weathering. So we know that the rise in the atmospheric CO2 is because of people. There's no doubt about that. But there's not as much CO2 accumulating in the atmosphere as we're putting there. So there's other action going on. One is uptake going into trees and the land surface in places that are not being deforested. And then there's uptake going into the oceans. So now thinking about this going into the future, we'll start out thinking about what the land is going to do in the future. And for one thing, it's really it's difficult to predict because we don't understand why the land surface is taking up CO2 today. So it could be CO2 fertilization, which plants grow better a little bit if there's higher CO2 because they have to get CO2 out of the air. It could be the longer growing season. Or it could be fertilizers. Either sort of runoff of fertilizers that we put on agricultural land and golf courses and things like that, or actually one of the things one of the components of acid rain. We've talked a lot about sulfuric acid, and that's like 2/3 of acid rain. But the other third is nitrogen. Nitric acid, which is when it lands on the earth is a fertilizer. So maybe this fertilizing from air pollution is causing the biosphere to grow a little bit. But if we don't understand why this is happening, it's difficult to project it into the future. And there is this problem with soil respiration faster in a warmer world. So all the soils that have lots of organic carbon in them are in the high latitudes where it's cold. So the organic carbon, the dead leaves and stuff like that, doesn't decompose because it's cold. Maybe it even freezes. Whereas the soils in tropical rainforests have very little carbon in the soils because everything decomposes so quickly in that hot weather. So if we make the planet kind of more tropical, it could be that we'll start letting all that soil carbon turn into CO2 in the atmosphere, and this thing could actually go the other way. And in a larger sense, the future of land carbon, it depends on land use, on how we, how much forest we cut down or allow to grow. So, you start to put people in, and it's, if you've got a carbon cycle model and you got people in it, all of a sudden that's a whole wild card, loose cannon. How are you going to, predict what people are going to do? It's sort of almost out of the realm of science, and now it's more like sociology or something like that. But then, in an even larger sense, there's this problem with inventories of carbon, that the land surface is just going to sort of eventually kind of peter out in terms of a carbon reservoir, because there's just so much more fossil fuel than there is land carbon. So coal is something like 5,000 gigatons of carbon, and sort of land surface living stuff is only 500 gigatons of carbon. And soils, which are mostly dead carbon, are maybe another 1,500 gigatons. But even so, if we were to take all of this 5,000 gigatons and burn it, the land is going to run out of steam in terms of how much carbon it can take. Because you can't make 3 times as many trees as you have in a natural world, or 3 times as much soil organic carbon or something like that. So eventually, the land surface kind of poops out. And what that leaves us with, in the long run, so we're talking now about sort of the impact over timescales, into the future, 100 years, 1,000 years, 10,000 years. You already know about the time scale for the silicate weathering thermostat is hundreds of thousands of years. So we're sort of thinking about the carbon cycle into the deep future, and most people who think about this kind of forget about the land surface, because who the hell knows which way it's going to go, and it's small anyway. So the big game in the carbon cycle on the long term is the oceans. So the ocean interacts with CO2 in the atmosphere by way of this pH chemistry that we talked about last time. So just in the interest of sort of making sure that this chemistry is on your radar screen as something that's important to sort of get familiar, get comfortable with, I'm going to put it up there again. The chemical reaction that happens when CO2 from fossil fuels dissolves in the ocean is it reacts with this species, carbonate. And a water to make, in this equilibrium reaction, 2 bicarbonates. So CO2, as we've already said, is an acid because it reacts with water to make carbonic acid. So if you add CO2 to the water, it reacts with the water, makes this carbonic acid, and the carbonic acid has these H pluses that can pop off, and H pluses are what make an acid an acid. That's what make it, you know, have its acidic properties. So so this CO2 then is an acid, and carbonate ion is actually, it neutralizes the acid. It's actually what they call at the drugstore an antacid. So if you've got a sour, acidic stomach, you know, you eat too much at Thanksgiving, you go buy a Tums. Tums are made of calcium carbonate. And this dissolves and it neutralizes the acid in your stomach and you feel better. They call this an antacid because it's like an anti-acid. It's like an anti-CO2. So the CO2 from the air goes into the ocean and it reacts with carbonate ion, which is like an anti-CO2. That's sort of where it goes. And it hides from the air in this form of bicarbonate. See, bicarbonate and carbonate ion both have these electrical charges on them. So that means that, you know, as they are, unless you neutralize that electrical charge somehow by reacting by adding an H plus to it, it can't evaporate to the atmosphere. So if you take a pan of water and you put some sodium chloride in it, some salt, some table salt, and then you boil it down on your stove all the way to dryness, when you get to the end, that salt will still be there because it's got electrical charges. It can't go into the air. Only neutral molecules can go into the air. So because these have charges, they kind of can't go in the air, and so the carbon reacts with this anti-CO2, the antacid carbonate ion, and goes to bicarbonate. And both of these, with their charges, sort of hide from the air in that way. So the ocean then can store more carbon than it would if there were no sort of buffer chemistry. So the way it works is that the higher the dissolved CO2 concentration, the lower the amount of carbonate. So they're kind of inversely related. They're like the two seats on a teeter-totter. One goes up, that means the other one has to go down. So fossil fuel CO2 dissolving in the ocean, you start out in an ocean that has lots of carbonate ion in it. But as you put more and more CO2 in there, you're changing the acidity of the ocean, because CO2 is an acid, and then the amount of carbonate ion decreases. So the lower the carbonate ion is, the less, the more depleted the buffer chemistry is. Let's say the weaker is the CO2 buffer. In other words, the ability to take up more CO2 gets kind of used up. How much CO2 the ocean can hold is determined by how much carbonate ion concentration there is. And when it's all gone for the time being. And so the ocean kind of peters out as a way of storing CO2. So when CO2 is released to the air, it dissolves in the surface ocean, and then the surface ocean undergoes this circulation where water from the surface sinks down into the deep ocean. Mostly that happens, almost entirely that happens in the very high latitudes where the water at the surface is very cold. Because the way to make water go to the bottom of the ocean is to make it denser than all the rest of the water. So it's cold water that's denser than warmer water. The warm water sort of floats on top, and CO2 goes into it, but that warm water doesn't really go anywhere. It sort of sits there and just kind of doesn't do anything. But when CO2 dissolves in these cold waters at the surface, then it can fill the deep ocean, and the circulation time of the ocean is something like 1,000 years. So eventually, the atmosphere and the ocean come to an equilibrium. The CO2 spreads out. So let's see. Let's make a plot of CO2 in the air, and we'll start out at some sort of natural level. So this will be our 280. So that's the value from ice cores from like the year 1750, before the CO2 started to go up. It was stable at 280 for thousands of years, and then it started to sort of rise up. And so we'll draw that rise as fairly quick, because now we have to have something like 1,000 years of time to let the atmosphere and the ocean kind of reach a new equilibrium. So the CO2 goes into the ocean and mixes throughout the whole ocean, and it takes 1,000 years, and it pulls the atmospheric CO2 concentration down. It doesn't go all the way back to 280 after 1,000 years. Let's say I'll put 1,000 years sort of right here. And then where it's going is into the ocean. Like that. So the really critical thing to notice here for today's, for the purpose of today's lecture, is that the CO2 doesn't all go into the ocean. Even though the ocean has a lot more carbon than the atmosphere does, like 50 times more. So if you didn't know anything about anything, you might say, well, the amount of carbon in the ocean is 50 times higher than in the air, so if I put some new carbon in there, 50 parts, 98% of it will go into the ocean and only 2% in the air. In other words, that the new stuff would spread out in the same proportions as the old stuff does. But that isn't actually the way it works. You put the CO2 in the air and you let it equilibrate, and something like 25% of the fossil fuel carbon is still in the atmosphere after the atmosphere and the ocean have reached equilibrium. And so if there was nothing like the volcano weathering and degassing and all of that, if the ocean was just this thing of water in a Teflon bowl or something, and there's no reactions happening, 25% or something like that of the fossil fuel CO2 would stay in the atmosphere forever. So after it's gotten here, the ocean is sort of acidified. Which I don't mean that it's acidic like battery acid or Coca-Cola or something like that is acidic. It's still pretty close to neutral, but it's just a little bit more acidic than it was before, and there's less carbonate ion than there was before, and the chemistry has changed enough that it might be noticed by corals and things like that, and it's changed in this way that it's sort of acidified. So after the CO2 equilibrates with the ocean, there's sort of a next stage to how the system kind of responds. And that is that there's lots and lots of calcium carbonate in the world, on the seafloor, in the sediments, and also on land. And it's always sort of being dissolved and reformed and everything. So essentially what happens is that calcium carbonate dissolves just like Tums, because the ocean has this nasty sour acid stomach, and it wants to and it becomes neutralized by dissolving calcium carbonate. So what this does is it replenishes the ocean stock of carbonate ion, which is our anti-CO2. So as carbonate ion comes back up to sort of natural levels, the corals are happy again, and the pH of the ocean is going back to where it was kind of originally. And additionally, as you put more of this carbonate ion back, the ocean takes a bit more of that fossil fuel CO2. So let's modify our time series here. I'll make it a little bigger. And so we're going to start out with natural, and then we're going to go up during the fossil fuel era, and we're going to come down in the course of sort of 1,000 years to about 25% is left of the fossil fuel CO2 is still in the air after 1,000 years. And then after that comes this calcium carbonate neutralization. So, you know, taking the Tums and neutralizing the acid. And so now this takes something like 5,000 years, more or less. Maybe 10,000 years, maybe 2,000 years. There are models of the carbon cycle, and they differ a little bit in how long they take to do this. But so over the course, so here now is ocean invasion. Is this first part. And then the second part is the calcium carbonate neutralization. And that takes place over thousands of years. And it pulls the CO2 down to just about 10%. Is the airborne fraction of all the fossil fuel that's ever been released after some thousands of years. And then from here, you know what's going to happen already. It's going to be the weathering CO2 thermostat. Which pulls the CO2 down. Eventually, back, if this was an equilibrium before, it sort of returns it to the natural value. And this takes something like 500,000 years. So this sort of long response, this long cleanup time, we call this the long tail. Of the CO2, of the global warming climate event, essentially. Now, I was going to show you a picture from the past. I'll hopefully show that to you on Friday, that shows a CO2 excursion, and then it took 100,000 years, which is, you know, pretty close to 500,000 years to neutralize the CO2. And there are lots of models, carbon cycle models, and they all predict this long tail. But somehow things have gotten kind of screwed up in the way that science is, this particular little tidbit of science is sort of presented to people, in that somehow everybody has the impression that the whole thing goes away in just a few centuries or maybe 1,000 years. So a few centuries and it would all be over. So for example, I mean, there's a whole bunch of books. Every book that's written about climate change, if it comes up at all, they tend to have this wrong. And so in Hot, Flat, and Crowded, it says, it says here, CO2 stays in the atmosphere for several thousand years, which, you know, is better than the book I used to have students read, which was called Field Notes from a Catastrophe by Elizabeth Colbert. And she said it stayed in the atmosphere for several centuries. Well, so, you know, several thousand years, 500,000 years, linguistically, maybe several could be 500, I suppose. I don't know. It seems a little deceptive to me. I'm imagining, you know, Friedman always talks about sitting in a cafe in Bahrain and talking to the chairman and CEO of some company or whatever. I'm imagining, you know, hey, Friedman, I'm a little short today. Can you buy me a sandwich? And I say it just costs several dollars. And then, you know, so he buys me a sandwich and I eat it. And then the bill comes and it's $500. And I wonder if Friedman would feel, you know, ripped off in that case. I think that saying several thousand years is sort of wrong. I think that's sort of misleading enough to be wrong. But it's a very common mistake that is made. So I actually, sort of in the interest of disclosure and clarity here, wrote a book which was trying to correct this point. It's called The Long Thaw. And I'm not asking you to read it because all the information that's in there that we're talking about in lecture here is also in the textbook. So, you know, don't feel like you have to go get that book. That's kind of a book for popular, you know, for grandmothers and mothers-in-law and things like that to read, not for serious science undergraduates or, you know, serious undergraduates doing your science class like you guys. The reason why I wrote the book is to correct this point. And it could be, you know, one could make the case that we're not going to live for 100,000 years, so why should we care? And in a practical sense, you know, maybe there's something to that. There's something called a discount rate in economics that says that some cost in the future, you can, instead of, say you've got a cost of $100 in 100 years, instead of just putting $100 under the mattress and leaving it there for 100 years to pay that in the future, you could take, you know, $5 or $3 or something and invest it in a bank account that gets some sort of interest. And so what it does is it takes that cost in 100 years and shrinks it down by a lot, when, you know, for how much it'd be worth to make that go away in today's money. So to an economist, 1,000 years, 100,000 years, forget about it. It's not on the radar whatsoever. But yet, nuclear waste has a long lifetime of tens of thousands of years or hundreds of thousands of years, and that seems to matter to people. So, you know, I wrote this book to try to, you know, make the point that when you fill up your gas tank, you're affecting climate for, you know, 500,000 years into the future. It's not sort of 100 years or several centuries or something like that. So what are the implications of this? Well, the first thing you got to remember, and you're now very well situated to understand this because you're becoming very well informed about the physics and chemistry of climate, is that the first effect, it has to do with the band saturation effect. And what that says is that if you had CO2 concentration and then the temperature of the Earth, you add a little bit of CO2 and you get a lot of warming. But as you add more and more, the warming kind of decreases like that. It doesn't, you get less sort of bang for your buck as the absorption bands for CO2 get more and more saturated. So that means that a little bit of CO2 has a bigger effect on the temperature than you know, per CO2 than a big one. So if we take that effect and draw a temperature plot that goes with this CO2 plot, so I'm going to draw it sort of with the same axes here, and now it will be the temperature of the Earth. You get warming, you know, the highest warming is when the peak is there, when the highest CO2. But as the peak sort of subsides into the long tail, the amount of warming you get from this much CO2 is more than looking at it in the CO2 plot. So the temperature might look sort of like that. So in CO2, it's sort of like peak, mostly peak plus, oh yeah, there's some tail that's kind of like an afterthought. But you know, mostly you can say, well, it's the peak. That 75% of it goes away after the peak. So you know, we'll just kind of simplify things and say it's all done at that point. Whereas when you're looking at the temperature, it looks like, you know, mostly tail plus, oh yeah, there's a little peak there, you know, at the beginning. So it tends to emphasize the tail. When you look at it in terms of the climate impact, because of the band saturation effect. So there are various parts of the climate system that take a long time to respond. And the most obvious example is sea level and ice sheets. So we'll talk in the next couple of lectures about what the forecast from IPCC for the next 100 years is in terms of temperature and sea level and stuff like that. And you've already seen quite a bit of that in the 6 Degrees book. But if we think now just in sort of the longest time frames, there's a figure in the textbook that shows how sea level varies as a function of global temperature as you look back in the geologic record. So not projected just for the coming 100 years into the future when it takes a long time. You know, it takes a long time for ice sheets to change their size, maybe thousands of years. So ice sheets, the big ice sheets, are not really a big part of the forecast as it stands now for the next century for sea level. But looking at it over geologic time, there are huge changes in the sizes of the ice sheets. So the big ice sheets are the ones in Greenland and in Antarctica. And together they hold enough ice today to raise sea level by something like 70 meters. So you know, that's a huge change. Okay, so here's today. And so the global average temperature of the Earth today is about 15 degrees C, and sea level is defined as 0 meters. Here's the last glacial time, which was 20,000 years ago. And the temperature of the Earth was about 6 degrees colder than today. So 11 degrees C. No, 9. 15 minus 6, 9. I can do that. Even standing up in front of people, I can still do that. And the sea level at that time was 120 meters lower than today. And that's because of all the ice, especially in North America. The Laurentide ice sheet was a huge ice sheet. North America looked like Greenland during the last ice age. Just a huge mountain of ice. And the sea level was 120 meters lower than today. There are other points going deeper into the past. So there was a time about 3 million years ago when there wasn't really much of any ice in the northern hemisphere. Greenland hadn't really, come into full blossom yet as an ice sheet. So temperature was a few degrees warmer, maybe 1 or 2 degrees warmer, and sea level was 25 meters higher than today. And then there are times, sort of in deepest time, that we talked about, sort of hothouse climates, times when the CO2 concentration naturally, just because of the vagaries of the weathering CO2 thermostat, you rearrange the continents, or you build some mountains, or you put some plants in there or something, you can change the set point of that thermostat, and you can dial it up. And so there were times, lots of times in Earth history, when there's basically no ice. And so something like 40 million years ago, there was no ice, and sea level would be, as I said before, 70 meters higher than today if you were to melt all the ice in Antarctica and Greenland. So, you can, there's a lot of complexity here, and people spend their whole lives studying the last glacial maximum, one particular ice sheet or whatever. But you can also just kind of cavalierly, connect the dots, and you see this strong relationship between the temperature of the Earth and sea level. So for comparison, the IPCC forecast for the year 2100 on this plot would be right about here. So 2100, 3 degrees C of warming, and half a meter of sea level rise. So we'll talk more about the forecast beginning in the next lecture. But most of this, so this sea level rise in the next 100 years, half of that is caused by just warming up the ocean. So the water expands, like the mercury in a thermometer expands, and so it rises up and goes up past higher numbers. That's sort of like sea level. The ocean is like that mercury, and you expand it and it rises up. And then the other half of this half meter is from little tiny glaciers like on mountains in the Andes and in Alaska and Glacier National Park, places like that. So, this forecast for the year 2100 is not on this line from the past, and that's because of the presumption that it takes longer than 100 years to really clobber those big ice sheets. But in the long term, since there's lots of time, 500,000 years is plenty of time. The ice sheets come to equilibrium in a couple thousand years. The ultimate sea level forecast for, resulting from business as usual, given this long tail, could be 100 times worse than what they forecast for the year 2100. So, the year 2100 is just not the right time scale to talk about ice sheets. It's kind of like if somebody is standing, on a ledge of their building and they're going to jump, and you're trying to be helpful, so you say, hey, if you jump in 10 milliseconds, nothing bad will happen to you. Well, that's because it takes longer than 10 milliseconds to hit the ground. It's not particularly helpful information. By saying in the year 2100 sea level only rises by half a meter, it sort of misrepresents kind of the full impact of the CO2. So that's what the long tail is about, and the long thaw. So we'll leave it there and come back on Friday.